Stanford University.
I'd like to welcome you all to this evening's lecture. My name is Brian White, and I'm chair of the Stanford Mathematics Department. This lecture is one in a series of public lectures organized by Stanford's Mathematics Research Center and by the Friends of Stanford Mathematics. Today, if you're interested in coming to such events in the future and are not on our mailing list, please send me an email and we'll add you to our list. Today we are very fortunate to have as our speaker Professor Tadashi Tokieda. Professor Tokieda is a leading expert in applied mathematics, particularly the mathematics and physics of fluids. He has had a very unusual background. He started out in classical Japanese painting and has had his work exhibited in galleries in Tokyo. Next, he trained as a linguist, first in France and then at Joshi University in Tokyo, where he completed bachelor's and master's degrees in classical philology. He speaks many languages, including Japanese, French, Spanish, Russian, Greek, Latin, and Finnish. If you've ever had the good fortune to take a math class from Professor Tokieda, you'll find that he often stops to discuss the etymology of terms that come up. After his degrees in philology, Professor Tokieda became interested in mathematics. He did a second undergraduate degree, this time in mathematics, at Oxford, and then got his PhD in mathematics at Princeton in 1996. He's now Director of Mathematical Studies at Cambridge University. This year, he's at Stanford as our Distinguished Visiting Poincare Professor. In addition to his mathematical research, Professor Tokieda is very involved in mathematical outreach. In particular, he's famous for his toys, which have been featured in Royal Society's summer exhibition in 2007 in London and at the Sorbonne in Paris for the Henri Poincare Centennial. He regularly teaches at the African Institute of Mathematics in Cape Town, South Africa. Many of you had the pleasure of hearing Professor Tokieda lecture in this series last year. Please join me in welcoming him back.
Thank you. As we go through life, every once in a while encounter numbers that look significant, but which we can't quite place. Do you recognize this number? 3.1415 and so on? Yes? What is it? Yeah, it would have been pi if that digit was 7 instead of 4. And what about the next number? 299 and so on? That's right. Yes? Excellent. It's the speed of light in vacuum in meters per second. And then every once in a while, you also encounter numbers which I almost recognize but can't place. For example, when I saw this number, I knew it from somewhere, but I can't, I mobilized my entire scientific education and I still can't place it. And finally, Eureka, I know what it is. Of course, that's the telephone number of the Stanford Math Department. And finally, the topic of this theme, leitmotif, shall I say, of this lecture, is 2.5. 2.5 has the distinction of being the number between 2 and 3, and I'd like to convince you that that is natural, in some sense, dimension in which paper or any membrane, any surface evolves. By itself, it is two-dimensional in extent, but also it will be important that it lives and evolves and shows all sorts of mysteries in the ambient three-dimensional space. This interplay between extrinsic and intrinsic, 3 and 2, is going to be the theme of my talk. Camera, please. I brought here a paper with a hole and also a circular coaster. And if I fold this paper in a certain fashion, I can pass this coaster through the hole. I haven't started cheating yet. It is really going through. And it can even go backwards, you see. But when you open one against the next to the other, you see that the diameter of the coaster is clearly larger than the diagonal of the square hole. How did the coaster go through the hole? Well, it was really going through. I just go in. It's all. It's really going through. And yet, clearly, what's going through is larger than what's allowing it to pass through. How is this possible? It's all in the wrist, of course. You see, and I'm going to reveal this secret for free because you're such nice people this evening. When you fold the paper first in two, that's kind of a two-dimensional operation, the largest gap which you can exploit in order to pass the disk is, of course, this gap, which used to be the diagonal of the square. But then, having done this, I start twisting the whole thing until those two sides line up with each other. And in doing so, you see that my paper starts moving in the perpendicular direction, in the three-dimensional direction. It escapes into the ambient direction. And when these are aligned exactly, I squash and fold and shift by one. And then you get this thing. Now, the largest gap that I can use to pass the disk is this one, which used to be, lo and behold, the sum of the two sides rather than the diagonal. So if you remember Pythagoras, you gained an extra factor of square root of 2, which is a bit more than 40%. And that's why you can pass this disk whose diameter is larger than the diagonal, but smaller than the sum of the two sides. And also it's all in the wrist. And you can see that in this discussion, can we have the slides, please? What was visibly impossible became possible because we were resourceful enough to exploit the ambient dimension, not staying in dimension 2. So we shall come back to this theme time and again. Do you recognize this gentleman? He looks rather sad and romantic. Yes, he's one of the most romantic figures in mathematics. That's Évariste Galois, who died at the young age of 20. And then immediately several of you are thinking, Tadashi can't do arithmetic because if I subtract 11 from 32, that's 21, not 20. But he died just before the 21st birthday, so he was 20. Now, he left a gigantic legacy for all of us in mathematics. And one of the rather cute problems that he allows us to solve is a classical Greek problem. You might have a high school recollection of using ruler and compass, bisect, divide exactly in two equal parts, any angle. That is fairly straightforward. And you can ask, well, can you do the same thing with trisection? That is, given an arbitrary angle, using ruler and compass alone. That's the restriction. Can you divide that angle into three equal parts? The answer, Galois teaches us, is no. An angle that looks innocuous like 60 degrees is actually, turns out to be, it's provably impossible to trisect. However, we don't stop there. There is an ancient art of origami, that is paper folding. Ori means fold, and kami means paper, using which it turns out that you can trisect any angle, indeed, nsect any arbitrary angle. And once you notice this, actually, the operation is not that difficult. On the left, I indicated how you would bisect a natural angle. So suppose that you are given an angular sector as a sheet of paper. How would you bisect it? Well, you are going to fold one paper over the other, and then you arrange so that the edges align. And then once the edges are more or less aligned, you just negotiate and then squeeze the middle. And when you open, you have this beautiful line, which is the bisector of your angle, right? Well, how about trisection? It's very easy. Now you fold, but you overshoot and come back a little bit. And in this configuration, you arrange the sides, you negotiate until the edges are aligned, and then you crease. And when you open, you see those two lines coming out of the corner, and they are the trisectors of the angle. And in general, of course, n is easy. You go back and forth, crease, and that's it. It sounds like too good to be true, but it is indeed true. So origami allows us to do things that we hadn't dreamt of. Do you recognize this gentleman? That is indeed Gauss. He looks rather stern, although he lived a much longer life. And he also left a humongous legacy for all of us in mathematics. And one of the cute problems that he allowed us to solve is another classical Greek problem. You might have had a high school experience of using, again, ruler and compass alone, constructing a regular polygon. For example, can you draw a regular triangle that is equilateral triangle? Yes, you can. That's the construction. You just draw a line segment, and then you plant the pivot of the compass. You go whoop on from the other side, where they intersect is the apex of the triangle. And similarly, square, you can pentagon is a little tricky, but you can, and so on. So you can ask yourself, well, for which n can we construct a regular n-gon with ruler and compass alone? And the answer is a bit more complicated. It turns out what I'm writing there is not quite accurate, but it's accurate enough. So the answer is essentially those numbers, 2 to 2 to some small n plus 1. I put in front a power of 2, because you see, once you constructed, for example, a regular 5-gon, it's easy to bisect each of the sectors and then make it 10-gon. You can always double the number of sides. That's easy. So you can always jazz up the result by putting a power of 2 in front. But the essential part is this. These are called Fermat numbers. And if you put various powers here, you get a strange sequence, 3, 5, 17, 257, and so on. In particular, you can't construct an 11-gon, regular 11-gon. That's impossible. But you are beginning to suspect already that with origami, you can do all n. And I'd like to, camera please, show you how to do this by beginning with a regular pentagon. 5 is on the list, so it's not that impressive, but it is the idea that's quite interesting. So you take a strip of paper, and then you make the simplest knot that you can imagine. Yeah, that's the knot. And then you tighten the knot while squashing it flat, and tighten and squash it, and you tighten and squash it, and you keep negotiating, tighten and squash. And when it's completely tight and completely flat, what you obtain is this shape. In order to show you what's happened, I'm going to stuck in what's sticking out. And you'll see that what we have really obtained is a regular pentagon. The wonderful thing about this operation is that I didn't have to think. Nature took care of this miracle. And it is a wonderful exercise to show that it is, in fact, rigorously a regular pentagon. And if you have the fortune to go visit Japan and stay in a traditional inn, you know that they lend you traditional pajamas called yukata. Very nice. And also a belt made of cloth. And it is a tradition in Japan, in some regions of Japan anyway, to fold the belt in a pentagonal pattern and then offer it to the guests. So it's a very ancient thing that has been known. Well, 5 was on the list of constructible polygons, but what about 11? This is 11, and I hope that you are convinced. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 gone. And that's, according to Gauss, not constructible with ruler and compass, but with origami, you can. And it is essentially the same construction. What I mean is the following thing. Can we have this slide, please? You see, on the right, you see the 5-gon. And you made this by passing through itself by making a knot. And you notice that I made one pass, the simplest knot. It turns out that if you make 2 passes, a slightly more complicated knot, 2 passes and then flatten, the knot that results in the middle gives you n equals 7. If you make 3 passes, n equals 9. 4 passes, you get to the regular 11-gon. Now, you might be complaining already because, well, already with 1 pass and simplest knot, we went up to n equals 5. What about equilateral triangle, n equals 3? We skipped this. Well, if 1 pass gives you 5, 2 passes 7, how many passes should I make in order to get 3? You should have a knot with 0 pass, and that's what it looks like in the corner. You come in, almost go through, but you don't, and then go out. And then in the corner, hidden in the corner, is a regular 3-gon equilateral triangle. So you can do this. And as I explained, this construction shows that you can do regular odd-gon for any odd number. And once you have odd numbers, you can always double. So any n can be accessed. Bisection is easy. OK. So far, we have been discussing geometry and pure mathematics in general. But we shall now transit very gently towards physics. And then later on, without you noticing anything, we shall transit to engineering and physics and so on. And the reason we are expanding our area of investigation is we must. We must because those phenomena that we have been discussing exist on all scales all over the universe. They come under different names depending on whether they're deliberately designed or randomly produced. Some of these are called origami. Buckling, do you know what buckling is? So buckling, you don't have to switch the camera. If you press a rod from both ends, initially, if the pressure is not too high, rod shrinks elastically, but at some point it can't take it anymore, and it buckles out. Yeah, that's called buckling. Or crumpling sheets of paper and so on, they come under all names. And here I have shown several examples from different scales. On the left corner is a very strange Japanese method of manufacturing paper called minowashi. And what you do is to crumple a sheet of paper and then put on it bitter essence of persimmon fruit. And then dry it, and then crumple, and then put the persimmon on it and dry, and you repeat it. And this has a wonderful property of strengthening this paper, so strong that you can make clothes, bags, and so on, even sandals and slippers out of this paper. And the secret is this intermeshing of microfibers on the scale of these wrinkles of the scale of less than millimeter. On the top right corner, you see this friendly animal. And his trunk, as you see, is full of wrinkles, lined with wrinkles. And there are good thermal as well as biomechanical reasons why those wrinkles are very useful. Wrinkles, or crumpling and buckling, can happen on enormous scales as well. Here you have the map of Latin America. And that's the Andes, this mountain range. What is a mountain range in this case? Well, it is simply a crease that was formed when the Pacific plate was starting to push against the American plate. And then eventually, the mountain range had to rise because it's a crease that you're making. It's a crumpling that you're making. Okay. By the way, I heard it claimed that, in fact, Amazon used to flow into the Pacific. And at some point, because the Andes started rising because of this creasing process, it's a giant crease, giant origami. At some point, the entire continent tipped the other way, and Amazon started flowing into the Atlantic. And it's within sort of an observable geological time scale. OK. So the challenge is, can we find any science, any laws of nature governing all of these, including a random case like this? You see, if you take a sheet of paper, crumple it, and open it, it looks like this. And it looks like a crumpled sheet of paper for the good reason that it is a crumpled sheet of paper. What I mean is, what is it that we're seeing? You see, if you ask an artist, even a good one like Leonardo da Vinci, to draw a crumpled sheet of paper, creases, it's extremely difficult. Da Vinci can't draw a crumpled sheet of paper. Whereas we, having lived in this universe for a number of decades, can instinctively recognize a crumpled sheet of paper. Mathematicians would like to say that this kind of pattern with lots and lots of creases, points and connecting edges and so on, is a graph, embedded graph. And there is a lot of information about whether each crease is a mountain fold or ridge, a valley fold and so on, length of the edges and so on. But it's an embedded graph. But not all embedded graphs, not all networks that you see like this, arises as a result of crumpling a sheet of paper. So what are the conditions? What are the conditions that a network must satisfy in order to be manufacturable by crumpling a sheet of paper? This is the question. And somehow, all our brains can process this and immediately recognize when it's a crumpled sheet of paper and when it isn't. But this is a new field of science. We don't really know. And as a present, I'd like to give you a little theorem that you can take home. We have a lion up there. And when I open this origami lion, this is the fold pattern. You don't have to pay attention too much to blue and red. Blue is ridge folds, and red is dotted lines, the valley folds. What's quite curious is that if you look at those vertices, those points where lines, edges meet, and count the number of edges that meet at each vertex, there's some pattern here. For example, here there are 4 edges that meet at this point, vertex, 4, 4. Here, as many as 8 meet. Here, 6 of them meet. It's always an even number. Yeah. Now, it's actually not too difficult to prove that it is always an even number when you crumple a sheet of paper. And at the end, in order to simplify the discussion, you squash it onto the plane, and then you open it. You always have an even number of edges meeting at every vertex. So please allow me to admit this, because I'd like to move on and show you something much more spectacular. But this is not too difficult to prove. It's just tedious to prove. For those in the audience who know such things, effectively, that's because, you see, when I squash it, I created something called singular covering, which has this pattern of front, back, front, back, front, back. And that kind of parity condition introduces this evenness. But anyway, so the simplest case is this: 4 corners, 4 sectors that defined by a crease. 4 angles, alpha, beta, gamma, delta. Those are 4 angles. And here, I'd like to give you this present of mine. It turns out that those angles, if they are produced by creasing a sheet of paper, cannot be arbitrary. They have to satisfy some condition. And the first condition that they have to satisfy is that they have to add up to 360 degrees. You wish you said it before, but I did. OK. The second condition is that the opposing angles, alpha and gamma, I'd like to remind you what that is. Sorry. Alpha and gamma facing together must equal in sum beta plus delta. And otherwise, you cannot make it by creasing a sheet of paper. And conversely, if that's satisfied, that's a result of crumpling a sheet of paper. In particular, a picture like this cannot be manufactured by crumpling a sheet of paper because the sum of this angle plus this is way too large compared with the other two. Now, camera, please. Let me prove this to you. First of all, there is a simple case which all of you have seen, which the origamists call the square fold. If you do this, you do this every day almost, 90 degrees everywhere. Of course, 90 plus 90 equals 90 plus 90. So it's satisfied. But if you are not so careful, you get a picture like this. Yeah. And in order to make this absolutely clear, I'm going to draw lines, traced lines, so that you can see where the edges are meeting at this vertex. Yeah. So those are the four corners. Can you see? OK. Now, let's call this alpha, beta, gamma, and delta. And you might have noticed that I wrote upside down. And, well, it came up right. Oh, that's very strange. Anyway, so it's alpha. So those are the 4 angles. Now, our business is to prove that alpha plus gamma equals beta plus delta. In order to prove this, this is a present, you can take it home. Let's go back to how this was made. This is alpha, yes? So seen from behind, that's also alpha. But alpha equals beta plus delta. Oops, I overcounted gamma. Did you understand this? No, I didn't. So let's do that again. So this is alpha from one side. That angle is also alpha. But this alpha on this side consists of overlapping beta and delta. But overlap is gamma. So alpha equals beta plus delta minus gamma. That's exactly the same thing as alpha plus gamma equals beta plus delta. That's exactly what it is. Can we have the slide, please? So that's the proof. And in general, if you have an even number of sectors meeting at a point, 2n lines, and the angles shall be called alpha 1 plus alpha 1, alpha 2, alpha 3, and so forth, all the way to alpha 2n, a necessary and sufficient condition for these to be manufacturable as angles of crumpling a sheet of paper are that they still have to add up to 360 degrees, and also that there exists some ordering of these in which this strange sum, which mathematicians call the alternating sum, plus alpha 1 minus alpha 2 plus alpha 3 minus alpha 4 plus minus closes to 0. You can rewrite this 4 case in that form as well. Alpha minus beta plus gamma minus delta equals 0. And the proof is exactly the same. What I'm saying is that if you, sir, give me a bunch of even numbers, an even number of numbers, and then they add up 360 degrees, and there is an order permutation in which this is satisfied, then I can manufacture it in the following sense. Well, I'm going to take the largest of alphas and start folding back and forth and back and forth and back and forth. And when I run out of the supply of angles, I know because of that 0 condition that I close exactly and I can squash and open up, and those are the angles. This kind of closing condition in mathematics is called sort of a cohomological condition, and it is an important sort of baby example of how we extract information in terms of cohomology from various natural phenomena. OK. But that was all still geometry, although we were crumpling a sheet of paper. But we crumpled so severely that there was only geometry left. Let's now prepare ourselves for the physics to come. Do you recognize this man? He's perhaps less romantically known, but he's equally important. His name is Poisson. And he looks rather happier than the previous two. Now, in preparation for what follows, I'd like to try to teach you half of what is called the theory of elasticity in about 30 seconds. So here we go. in elasticity, you consider often the following kind of problem. Suppose that you have a large block of material, and you squeeze it in one direction. And what do you expect? Well, this block is going to inflate, bulge out in the perpendicular direction. Right? How much it bulges out per how much you squeezed in is called the Poisson ratio. Similarly, if you pull, how much it tucked in its belly shrunk in this direction compared with how much you pulled out is called the Poisson ratio. Okay? Strictly speaking, you have to take the derivative, but that's the ratio. Okay. Now, the notation for the Poisson ratio in literature is a mess. You know, some people denote it by sigma, some people denote it by kappa. Those who should know better even denote it by p, and so on. It's really a mess. And after many, many years, my wife, Lisa Willis, and I thought about this and finally came up with the right notation for Poisson ratio. I mean, this is the God-given canonical notation for Poisson ratio, and it is this. Yeah. So, in 200 years' time, I would like the history of science to remember us as the people who finally found the right notation for Poisson ratio. Now, let's see some examples to see with our feet. So if you consider something like this, a unit cell, those black dots are supposed to be universal joints, and those greenish rods are supposed to be rigid rods. You can see readily that if you squeeze in horizontally along the blue arrows, it bulges out along the red arrows. That's a positive Poisson behavior, and if you put them together, you get this network or structure which behaves globally like that. You can also build a network like this, or if you like a clothing pattern, with hexagons as well. That also has the positive Poisson ratio in that if you squeeze in one direction, it bulges out in the perpendicular direction. That's positive Poisson. To be honest, Poisson ratio varies a lot from material to material, from structure to structure. But one thing seems to be very intuitive, which is that Poisson ratio should always be positive. In other words, it's difficult to imagine a scenario where when you squeeze a material body, it suddenly shrinks in the perpendicular direction, and when you pull, it expands in the other direction. Mind you, there are examples where the Poisson ratio is almost zero. Take, for example, a spring. You know, it's not perhaps a very good example, but here it is. If you squeeze the spring along the blue arrows, it doesn't look like it's becoming any fatter in the perpendicular direction, right? But actually, it is getting slightly bulging out. It's bulging out slightly. So the Poisson ratio is actually very close to zero, but if you look carefully, it is still positive. This opinion is also expressed somewhat implicitly by the greatest Russian authors of theoretical physics called Landau Lifshitz. They wrote a 10-volume series, which are the Bibles of the theoretical physics. And volume 7, I don't know why I took the French edition, that was the one lying around on my desk, is devoted to the theory of elasticity. And here, Landau is telling various good news to his students, who all have donkey ears. And there is a little footnote, which is a bit too small, so I'd like to translate on the fly. In fact, the coefficient of Poisson ratio varies only between 0 and 1/2. Okay? We don't know anybody in nature for which sigma, that's their notation for Poisson ratio. Do you know a good notation for Poisson ratio? Yes, thank you very much. It's alpha with a dot, right? So the Poisson ratio is negative, that is, which would bulge out while being pulled out. Faced with such a situation, of course, one's instinct is to try to construct structures with a negative Poisson ratio. And in fact, there are many of them. If you take a hexagon, but this time a dented hexagon, then in this picture, you can readily imagine this re-entrant corner that along the blue arrows, if you push along the red arrows, it will shrink as well. So you can put them together into a nice structure, and it will overall behave like this. So it will have an interesting behavior. For example, if you make clothes out of it, that if you pull in the vertical direction, it will suddenly become loose, and so on. Okay. There are many other interesting ideas. For example, here you seem to have a collection of just square blocks, but I connected those blocks by interesting hinges. This is a halfway model when I started opening it, and you see that those blocks turn in alternation, left, right, and while turning in this synchrony, in this dance, they open up as a whole. And this is, again, negative Poisson ratio behavior in the sense that if you pull in one direction, it opens up in other directions as well. Yeah. And you can do the same thing with the triangles, and there are 3D models available as well. Now, for isotropic materials, this is a little technical. Isotropic means that in all directions the material looks the same. It turns out that the limits of Poisson ratio are not between 0 and something, but it turns out that it's between -1 and +1/2. +1/2 is not too difficult to understand. It is the limit of incompressible case, and not to be confused with the incompressible case. What I mean is, if the material doesn't want to change its volume, yeah? If the body doesn't want to change its volume, that's what's meant by incompressible, where if you squeeze in one direction by, say, -1, there are two remaining directions. So the body must come out by half and half in order to compensate for the -1. Yeah? And in dimension D, if you're interested in that kind of thing, the Poisson ratio for the incompressible material would be 1 over D minus 1. Okay. The left limit, the lower limit, also has a physical meaning. And that -1 for isotropic material turns out to be the limit of unshearability. Now, I'd like to explain very briefly what I mean by this. Shearing means that you take a deck of cards and you put your palms at the top and bottom, and you move them parallel to each other, and you deform, for example, this brown square into this green parallelogram. Now, this shearing can be achieved in 2 steps. First, you take this brown square, and then stretch it along the diagonal and shrink it along the antidiagonal, which makes it into a losange. Having made a losange, you go stonk, rotate it a little bit, and put it in place. And the end result you see up to higher order errors is exactly the same thing as shearing. So you can do any transformation as a 2-step process. It turns out that if the Poisson ratio is negative, this first step becomes harder and harder to do. You see, because if you try to extend it along the diagonal, it also wants to extend it along the antidiagonal instead of shrinking. So you cannot do this first step, which gets in the way, so the material becomes more and more unshearable. With that preparation, we are ready to plunge into the wonderful world of physics. So this gentleman is still alive. He's an aeronautical engineer in Japan, Mr. Miura. And he came up in the 1970s, I believe, with a wonderful origami fold called Miura-ori. One example of which is given here. Can I have the camera, please? You know how annoying it is to fold a road map. Okay, many of you don't even know what a paper map is, but there used to be a map made of paper, yeah, or not on your apps. So it's really difficult to fold a paper map because opening it while you're driving a car to see which way is Palo Alto is okay. But when you try to fold it, it never folds back the right way, yeah? And it starts sort of creasing in the wrong way, and you're tearing, you make holes, and you go completely crazy, and the next thing you know, your car is in the tree because you're no longer driving. And the reason this happens is because there are too many degrees of freedom. But Miura-ori is this fold. And it has the wonderful property that when you just press 2 ends, it just collapses onto itself automatically. It has only 1 degree of freedom. It has absolutely no freedom to do any mischief. Wonderful thing. Can we have the slide, please? In Japan, you can buy maps made in Miura-ori. So can we have the slide, please? OK. Yeah, and it collapses or it opens up in a unique way. And it is notable that Miura-ori has negative Poisson ratio behavior. You see, you pulled it in one direction, it just opened up, and you just press in any direction, and it automatically collapses in all directions. It's quite interesting. And it also comes with this very low degree of freedom, only 1 degree of freedom, which makes this map very, very useful. Mr. Miura was an aeronautical engineer, and the original application that he had in mind was this thing. You know, one of the great problems of having a solar panel on an artificial satellite is that when you put it in orbit in a rocket, you have to store it in a really, really small space. But once in orbit, you want to open up this solar panel to receive the maximum amount of sunshine, and that's your electricity. But what often happens is that the way the solar panel is stored, when you try to open it, it goes clunk, 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 and gets stuck. Because there are too many degrees of freedom, you jam. And then you have lost an entire satellite, and it's a great loss. But the Japanese launched a satellite where the solar panel was folded in a Miura-ori. And then you can show mathematically that it's totally unjammable. You just start pulling 2 points apart, and whoop, spontaneously, it just opens up. Yeah, so that's a wonderful application of Miura-ori. May I have the camera, please, again? we have to face up to anisotropy, direction dependence. And as a warm-up, I'd like to show you a little magic trick. Those two sheets of paper were cut out from a single sheet. Those squares were cut out from a single sheet of paper, printing paper, which I collected from the Stanford Math Department. And I put them together with a paper clip. Yeah? And if I hold them like this, they stick together. Well, because they are made exactly of the same material, and they sag exactly the same way in gravity, so of course they stick together then. Yeah? But when I turn around, they separate. So on this side, they stick together. On the other side, they separate. I can start from the vertical configuration, and then as I tilt one way, they stick together, but the other way, they separate. That's very queer. But there's more. This is the separating side, yeah? And turned over, it became the sticky side, you remember? Now, let's keep this on the separating side, and let's make the clip migrate to the next edge. This was the separating side a moment ago. When I support everything on this edge, this time they don't separate, they stick together. And what used to be the sticky side now separates. This came about because we were interested in anisotropic structures. And roughly speaking, what's going on is the following. We thought that the paper should be anisotropic, if only because of the modern method of manufacturing paper, you pull it out of a big roller, so that introduces some graininess. And in the end, this direction and this direction of paper may not be completely equivalent. Now, for all intents and purposes, this non-equivalence is both invisible and immaterial, except to the professionals of printing and so on. But you can make them bring out in the following fashion. Because I like toys, this is a toy, but I brought a toy of this toy. It's a secondary toy. If you crease the paper like this, it's still flexible in this direction. But in this direction, it becomes stiff. Yeah. That's the well-known principle of corrugated surface. But for the mathematicians among us, I can labor the point by saying that I've already curved it in this direction. If I try to curve it in another direction, I would introduce non-zero Gaussian curvature, which I cannot do without violence to the paper, which to begin with had zero Gaussian curvature. It's an isometry invariant. So the Gaussian curvature is rigidifying this. Or in other words, whenever you crease something, whenever you sort of introduce a crease, you make it really flexible in this direction, but in the direction of the crease, you suddenly rigidify. It is an interesting mechanism. So I don't know what this sheet of paper looked like in terms of microscopic structure, precisely because they are too small. But it doesn't matter. I cut out two squares, and when I assembled them, I rotated one on top of the other by 90 degrees. And on this toy model, you see very well what happens. If I support them like this, the stiff one is supporting the flexible one on top, so they stick together. Whereas when I turn around, they can separate because the flexible one sags, but whereas the stiff one sticks out straight. And if I move to the next edge, the separating and non-separating sides exchange their roles. It's exactly what's happening. In retrospect, this kind of behavior can be shown, can be noticed in many, many walks of life. I don't know if in the long history of Stanford Math Department, I am the first lecturer who shows toilet paper to the audience. This was picked up from down the corridor. And when you try to tear it along this length, it tears very, very nicely, yeah? Very, very straight. But in this direction, you can't tear it. It's really difficult to go straight. And that's because there is really a microscopic but very pronounced anisotropy, which makes it somehow fibers are aligned this way rather than this way. Now, I couldn't help noticing that the Stanford toilet paper easily tears along the length, but not across. But when I said that, Ada Eliashberg immediately responded, but of course, because you want the paper to be tearable only along the perforation. Aha, yes, well, I become smarter every day. Okay. Can we have the slides, please? Let's discuss then the topic which is really dear to many of our hearts. Here's a large sphere. Can we put this large sphere in a small sphere? The answer is yes, you just shrink everything. But can you do it isometrically? That means without changing any length. You see, when I sort of make origami, I'm not changing length along the paper. I'm sort of folding them together and sort of creasing them so on, but I'm not changing any length along the paper. But can I do it for a large sphere inside a small sphere. By the way, for a circle, you can just wiggle the circle and put it in a small circle. That's no problem. But can you put a large sphere into a small sphere? That is the question. And the answer had better be no, because the curvature, Gaussian curvature, which made a fleeting appearance earlier, gets in the way. You see, when you dent something, the sphere originally had positive curvature everywhere, but along this ridge, you get zero curvature, so you change the curvature. And the curvature is an isometry invariant. In other words, you cannot do this without stretching or shrinking the surface. You may not notice this, but in this photograph, for example, you are sure, for sure, you are stretching or shrinking the surface. But hey, if the curvature is getting in the way, some people thought, that's interesting because curvature needs two second derivatives to be defined. So why don't we do this with only one derivative? You see? Then, you see, if you have a surface with only one derivative but not two derivatives, you cannot define curvature. Therefore, curvature does not exist. And what doesn't exist will not bother us. It sounds like cheating, but in fact, this was achieved theoretically by Nash and Gromov and others. A big sphere can be put inside a small sphere, it turns out, with C1 and not C2 class. In other words, with only one derivative. It's some sort of a strange core surface. And concrete construction was, by nested corrugations, was realized by Borelli and Thibert. And this was 3D printed in Grenoble. And this is what it looks like. It's an interesting thing. It sort of has some sort of twisted corrugation. And the large picture shows what it is. You see, not only do you have corrugation, but on each corrugation you have more corrugations. And on each of these you have more corrugations. You have a nested structure, sort of scaling, not quite fractal, but fractal-like structure. Can we have the camera, please? Now, it so happened that I was thinking about this kind of thing, but not from the mathematical point of view. And I discussed it with Borelli, and I have the impression that we could have asked nature to produce this result. So I'd like to show you one very unusual way of buckling. I take a sheet of paper with two glasses, and glasses must be a little far apart. And I roll the paper around those glasses, okay? Roll them tightly. And once I twist them, okay? And then I put them crease. And what you see inside is this pattern. And what you see when you open up is this pattern. It is really a beautiful pattern. And it has the property that when you push, it twists and shrinks and accommodates itself into a tighter corner, smaller corner, because I made it that way. Yeah. And you see, you cannot help noticing the similarity between this pattern. From the other side, it's even more beautiful. And the Borelli and the Nash, Kuiper, Gromov, and Borelli and Thibert construction. So if nature wants to put a large surface into a small surface, one of the ways of doing it is this twist buckling. And then you get sort of nested versions of this. And I think that's an interesting thing to notice. Can we have the slide, please? Oh, can we have the camera, please, again? Another example of buckling, or this kind of crease origami that I'd like to present to you is Momotani carpet. This is the example. And it's a variation, in some sense, of Miura-ori. I'd like to show you that. I folded this from a sheet of paper about this large on a long flight between London and Cape Town. And I started, and then started folding, and my neighbor looked a bit alarmed. And you can even see from that flight a little coffee stain in a corner. When I pull this object, what it does is this. And very prettily, what's happening on the back is dual to what's happening in front. It's made of a single sheet of paper. Yeah? And it also has this surprising, unexpected property that you see it's made of paper, and yet it has effective elasticity. You see, it bounces. It has effective bounciness. I mean, paper doesn't have bounciness, but somehow folded in this pattern, it's bouncy. It expands in all directions. Again, negative Poisson. OK. Momotani carpet. Can we have the slide, please? Let's look carefully to conclude at some amazing properties of Miura-ori. As we saw, it can open up lots and lots of possibilities, it and its variants and cousins and siblings, to lots of physical and engineering explorations. But what are the properties, what are the secrets of Miura-ori? The best reference that I know is by Jian Wei and Mahadevan. And this is a nice Miura-ori that was folded by Jian a few years ago. in order to simplify the discussion, I'm going to assume that, you see, Miura-ori is a collection of parallelograms. Let's assume that each parallelogram is a losange. In other words, all the edges of the equal length. So you have something like that. Then a Miura-ori, when it's sort of half open and so on, can be characterized by two numbers. One of them, constant, is alpha, which determines what the shape of each facet is, this losange is. The other one, variable, theta, that angle, is how closely folded together those two neighboring facets are. So when theta is 180 degrees, it's completely open and flat. And when theta is 0, the Miura-ori is completely closed. Yeah? OK. So in any state, shall I say, of Miura-ori, you have those two numbers, alpha and theta. Now, in this state, alpha and theta, it turns out that the Poisson ratio in that state has this expression. Don't pay too much attention to detail, but notice that you are subtracting a product of signs. Actually, 1 over square of the product signs. Sign is less than 1. So this term is actually greater than 1. So if you subtract from 1, you get something negative. Also, you notice that by playing with alpha and theta, you can actually make this number an arbitrarily large negative number. You can get every negative real number by a Miura-ori as the Poisson ratio. Now, you might think, but earlier we mentioned the proof, we mentioned the statement, theorem that the negative Poisson ratio can be only larger than -1. But that's isotropic case. In this case, there's a lot of anisotropy. And in the case of direction dependence, you can get arbitrarily large negative numbers. OK. At the same time, there is something really strange going on. We discussed this buckling pattern before. But that was a one-dimensional buckling. You know, I'm compressing a rod along its length. Suppose that you do the following experiment. You have a large membrane, and at each point of the membrane, you apply an isotropic and homogeneous contraction or compression. How do you do that? Well, you can wet the whole thing. You can sort of put temperature variation and so on. But anyway, you can shrink the whole thing. Well, how does the membrane, how does the surface react? In the beginning, it shrinks a little bit elastically. But at some point, it cannot stand it anymore, and boom, it sort of buckles out in the perpendicular three-dimensional direction. And it turns out that the natural buckling pattern that you see is the Miura-ori. So again, we could have asked nature to invent Miura-ori without waiting for Mr. Miura. So in the light of those two things, that every negative number can be realized as the negative Poisson ratio of Miura-ori, and that the Miura-ori is the lowest buckling mode of a surface, we can conclude that actually Miura-ori is certainly the simplest, but also the most universal model of negative Poisson ratio. Arrived at this point, we realize something even more beautiful, and in fact, which allows us to be totally lazy. In fact, there is a much easier way of realizing negative Poisson ratio without all this design issue. What we do is simply this. Can we have the camera, please? Yeah. And when I pull some parts, you see it expands in all directions. Because I made it this way, I compressed it in all directions. This is negative Poisson behavior. OK, so it has a lot of details. But on average, on the large scale, it is negative Poisson. And it looks terribly random, doesn't it? Yeah? It's a really generic probabilistic phenomenon. So can we have the slide, please? Just crumpling a sheet of paper produces negative Poisson ratio amazingly over a large scale and on average. So because those crumpled sheets of paper, OK, there are some conditions such as that angle condition that we discussed earlier, we proved earlier. But apart from those angle conditions, it looks as random as we can wish for. Well, people used to think, until not long ago, that the negative Poisson ratio didn't exist. Poisson ratio had to be positive. But contrary to that assumption, far from being experimentally freakish, maybe it is the case, this is a bold conjecture because it's written in bold, that randomly generated structures may have negative Poisson ratio in the majority of cases. That would be really an interesting thing to investigate. We started with playing with some numbers, so let's conclude with some numerology as well. I don't know who decided this, but in this part of the world, a lecture is supposed to last about 50 minutes, and that's 3,000 seconds, yeah? 3 times 10 to 3 seconds. So that's how long a lecture typically lasts, and our lecture lasted almost exactly that time. Do you know how many seconds there are in a year? Well, it turns out that there's a wonderful mnemonic which I use in order to convert units in astronomical calculations. It turns out that 1 year is almost exactly equal to pi times 10 to the 7 seconds. And you can do the arithmetic at home. The error is less than 0.4%. In case there are some people who knew this, let me point out that if you replace pi by square root of 10, square root of 10 times 10 to 7 seconds, in other words, 10 to 7.5 seconds, the error drops down to less than 0.25%. It's even better. Anyway, so it's about 3 times 10 to 7 seconds. And if you multiply that by 100, you see that 1 century is 3 times 10 to 9 seconds. Yeah? 3 billion seconds. 1 talk is 3,000 seconds. If you divide one by the other, it follows logically that 1 talk is exactly a microcentury. Did you know this? So next time you go to a lecture like this, you think to yourself, I'm going to spend a microcentury. For your generous company in the last microcentury, I'd like to thank you and allow me to wish all of you very cordially a very happy holiday season.
For more, please visit us at stanford.edu.